Hi, I'm Andrew, and this is IoT for lazy pet owners. Just wanted to do a quick acknowledgement of country. I'm here in Perth, and that's the traditional land of the Whadjuk people. So I wish to acknowledge the traditional custodians of the land we're meeting on, at least virtually, the Whadjuk people. I wish to acknowledge and respect their continuing culture and the contribution they make to the life of this city and this region. Who am I? Well, my name's Andrew Van Dam, and I'll be the first to admit I'm a jack of all trades and a master of none. I've done a whole range of weird and wonderful things before coming to the cloud. I did a lot of control and data acquisition systems for high voltage substations, industrial control with things like PLCs. I founded a machine shop. I worked as a mechanical fitter. My worlds make Boilermakers laugh, but I've done a fair bit of mechanical stuff there. A big part of my background as well is doing robotics and data acquisition for research organisations, including the University of Western Australia. That massive machine in the middle is a geotechnical centrifuge, so it's about 100 G at that payload there. That was an interesting challenge. I'm also a software engineer. I'm an AWS developer associate. I was CTO at a company called Tapeark, and we're moving petabytes of data into the cloud there. So things like snowballs, tape drives, etc. But most of my work has been in electronics. So that's designing circuit boards, firmware, testing, medium scale manufacture, all that sort of stuff. And it's kind of hard to talk about electronics today without talking about IoT. And I've been doing IoT for a while. It's sort of it's really become a buzzword around 2014. And I was doing it all the way back in 2012. So that's my way of giving this jack of all trades a bit of credibility. And that was back using GPRS. I was using things like PHP in the back end and databases, etc. So it has come a really long way, and that's why I'm excited for using things like AWS IoT Core, because it's made a lot of what I've found challenging in the past much easier today, especially now that IoT, as you can see in the last 5 years has taken off. So I'm an uncool IoT engineer. So obviously I'm on all the socials and stuff like that, and the reason I give this meandering background is because I think it's great to sort of show that you don't have to have been coding and building stuff in the cloud or big software systems for 20 years to start leveraging AWS and all this really cool tech. You can come into it, and in a very short amount of time you can make some really impressive systems. So what I'm talking about today is the Bikimatic. And it dispenses bickies in a matic fashion. I'm a really lazy pet owner. I love to automate things. And as a really good Douglas Adams quote that I'm going to butcher, but essentially, if a job takes 3 hours, but you can spend 3 weeks automating it, so you don't have to, you haven't really had to do the task. So I'm a lazy pet owner, but pets are a fantastic thing to have in your life. After the year we've had, I think a lot of people have had a lot of comfort in their pets and a lot of solace. But this particular one I'm talking about is a special creature. This is Olivia, and this is going to be the song of her people. Really good. It's about 6 o'clock on a Sunday morning. She has a magic ability for detecting when you're just waking up. So I decided I'd like her sleep in occasionally, and that's where I developed the Bikimatic, an over-engineered solution for dispensing cat biscuits from the comfort of your bedroom. It uses a whole stack of technologies. You can see here we're using things like S3, we're using API Gateway, Lambda, obviously IoT Core, as well as a whole bunch of electronics and other stuff. I'll give you a demo of the system in a second. But there is a competitor, obviously. This is a dense space, and the competitor has a couple of advantages as well. but it's a little simpler. It's a clock, basically. You stick an AA battery in there, you turn the dial around to where you need it in the timer, and at that point it pops open. Probably a better solution in some ways, but that's not what we're here to do. We're here to over-engineer a problem, and that's what I did here. And one of the things I really wanted is I wanted something that was closed loop control, so versus the open loop of that system. I wanted to know that I could get feedback on how much was being fed to the cat. I wanted to be able to do it automatically, and I wanted to know how much was actually going in, that it had actually been fed. For those that haven't done a lot of work in control systems, this is open loop where you kind of think something has happened. Closed loop is you have systems of measuring and actually knowing that it's happened. You could make an analogy between UDP and TCP, same sort of thing. So that's what this is. This was meant to be a closed loop feedback capable system. Intrinsically reliable, it's got a hopper there, globally controllable, and sort of a bit of continuous delivery. You can update and change it. But more importantly, it's a learning opportunity. So through the wonderful world of pre-recorded presentations, I've got a demo that I've prepared earlier. This is the Bikimatic, a wonderful creation of PVC and 3D printed parts. This is the feeder part itself. Now you just have to imagine there's a hopper here that's somewhere between this house and my last house. Doesn't matter. But inside here you can see we've got an auger. So that auger does the actual feeding. And we have a measuring hopper, this part here, that does the dosing. So there's a IR sensor at the top that can work out how full this is. At the very bottom there's a shutter with a stepper driven by a stepper motor, and there's a small button in the back that can detect when this is properly closed and homed. And then there's a mess of chaos in this little container here. So that's the ESP32 microcontroller, and then DC motor controller for the auger, and stepper motor controller down here. So it's already plugged in, so I'll pull it out. Just runs off 12 volts. Stick it in again. And you just saw that close this part here. So I did a homing routine, and now it's online and ready. So there's a few debugs via the serial port. And now via the website, we can just hit feeder. Done. So now it's going to close. And you can see it prepares the next dose. So that's the Bikimatic in a nutshell. And I'll go quickly over some of the hardware sort of mechanical parts, because that's obviously not the nature of today, is to talk about mechanical engineering. One thing I tried to do was only 3D print parts that I couldn't buy, because obviously PVC parts that I buy will be stronger, generally better toleranced, and they're also cheaper and easy to replace. For example, the hopper that's disappeared is a couple of dollars to buy down at Bunnings. One thing I will say about 3D printing is it's totally changed some parts of manufacturing that just in massive ways. A good example is Prusa, the 3D printer manufacturer. A lot of their product is actually 3D printed, but this means that even once they've released a new product, they continue to tweak and tune the design, both for improving their manufacturing speed, their reliability, reducing error rates, but also fixing errata and problems in their designs, which you can't do with mold. So that's really cool. I also modeled everything in Fusion 360. That way you make sure that all the parts fit together, including things like sensors, what the view angle is for the infrared sensor, for example. So you can do proper level sensing and stuff like that. So that's the mechanical elements, getting that closed loop for the hopper and that type of thing. Software wise, there's obviously some cloudy bits and there's some firmware bits, and we'll look at the cloudy stuff first. And this is the architecture diagram for that. So that web interface with the lovely picture of Olivia screaming is a static page served out of S3. Again, makes it cheap, easy, no problems there. And then there's an API call. that API call triggers a Lambda function. That Lambda function publishes a payload to a topic, which IoT core then passes through to the subscribers, which in this case is the Bikimatic itself. And you saw how tight that loop was. By the time I pressed the button, panned, it was already making the action. So very, very quick. Hosting an S3, cheap, easy, fast. Great way to go. The other stuff, so the Lambda API gateway and IoT. So IoT core and Lambda play really nicely together. I've used Python. You can see there's literally that not even dozen line of code there. That is actually what drives that function. It publishes the payload out to the topic, and that's it, done. One thing I will say, look at that code now, it should probably be QoS 1, so you have your different quality of service levels. 0 means it probably gets out there, 1 means it will probably go a couple of times. And I'll get to the advantages of QoS levels and shadows in a second, but it's not too daunting to trigger up and start to create these actions and flowing through if you're already familiar with something like MQTT, coming from an electronics background. And then coming from maybe a cloud background, there's some really good intro. So they're not two separate worlds. They overlap quite nicely. One thing I will use is in this example, I'm using just topics. So I'm just you subscribe to a topic. In this case, it's Bikimatic /feed. Instead of using a shadow. So obviously shadows and topics are related. But instead of using a device shadow here, it's been reduced the complexity. It's much easier to get up and running to actually start to see some activity, and it's easier to test. It's much easier to test just in the standard AWS console for IoT and the test dialog. You can just stick messages in, check the stuff's coming through, look at the debug levels out of your serial port on your microcontroller to see that your messages are coming through and how they're decoded. Going to shadows is much more complicated. There's not as much community support because it is an AWS niche thing as well, and it's starting to become a bit more industry based and not as many hobbyists are picking up and playing with it in this way. So there's not the great support for Arduino. So you can't leverage other libraries really well, and the other community stuff is nicely using shadows and getting to that more complex sort of Amazon FreeRTOS type of deployment. Speaking more, sort of going deeper into that firmware element, the actual hardware itself is an ESP32 microcontroller. They are awesome. I love them. This is this one here. This is a little development board. Focus. Go on. And that's less than $10 plus a bit of postage. It's got a full OLED color display, Wi-Fi built in, Bluetooth. It's incredible. They're so cheap now. It's never been a better time to get into electronics. Debugging isn't terrible. It's never going to be as good as a Python application or something you're running on a computer. You haven't got a full stack there, but it is much better than it used to be. Particularly if you're using something like Platform IO. Platform IO simplifies that a lot. And again, using Arduino. The Arduino libraries make life a lot easier. It's essentially a whole bunch of wrappers around C, but it allows you to port your code from one microcontroller to another without having to change where all the registers map to and those low-level type of things, because it is still very low-level type work. So the libraries that I'm using in this one is the Arduino library. I'm using a port of FreeRTOS, Amazon FreeRTOS, by a group called Explore Embedded, but it has very limited compatibility. It allows you to publish, subscribe, and connect, and that's it. There's no support in that, for example, for things shadows, which again gets back to that complexity. Once you start to go to a certain level, you probably need to start getting away from Arduino, and then you need to really start looking at heavier C requirements and stuff like that to execute. The architecture of itself, there's a whole bunch of little subroutines. It's actually not an overly complicated program. There's an I/O initialization, there's control for the DC motor, level sensing, all the Wi-Fi and MQTT, as well as a subscription callback for the topic, and a driver for the stepper motor. But the actual main event is basically a state machine, a whole number of states, and essentially once the device is started up, you see it booting. You saw that little homing routine. You can see here the motor sort of click that shutter closed. Then it fills with the auger. That's an internal control loop, detect the level, and it sort of fills and stops. And then it just sits idle until it gets that callback. So here you can actually see when we initialize the IoT. So we sort of connect to Hornbill, so that's the port done by the Explorer Embedded Group. Connect all our clients and keys. We subscribe to the Bikimatic /feed topic, and then we have the sub callback handler, which is a function called sub callback handler. And essentially what that does, and I think I've got it. I came on prepared. That sub callback handler is actually essentially changes the state, so it changes that system state from idle to dispensing, and that gets picked up here in our state machine. So it's actually a little bit out of frame, but you can see there's a dispensing, homing, filling, etc. And that's essentially, it goes through that and then goes back across. There's a fault state and stuff as well, but you can see that this isn't actually full closed loop. There's not a lot of data going back. And that's because you start to run into limitations with shadows versus pub sub, and the architecture starts to become more complicated. So, did it work? Yes. Well, you saw it running there a second ago. It sort of runs nicely off the app. It's super reliable. One advantage of microcontrollers is that generally, if it works, it works. You're not going to run into a lot of error states because you've got no real stack. There's no kernel. In a big way. If you're using a FreeRTOS, there's a bit of a kernel, but nothing like you're used to on larger systems. So you don't tend to hit rate limits or anything like that, which is a bit reassuring, especially with something this complex, without this much complexity. How do I actually implement this in the real world? It turned out that the planning was a bit easier than developing this over a longer period. But it was good fun to sort of go through and work, and it continues to be an interesting project. So what is next to that? So the next is the Mark K9. So we have a dog, Moose. His food's a bit bigger, but the advantage of this is that I can just scale it up. So I scale up the 3D prints, and everything else is the same. So I might want to change the background picture on the website, but that's probably it. But definitely want to now look at using migrating to shadows as really sort of anything more than a couple of publishers and subscribers. You need to start implementing shadows, and you can start to take advantage then of things like level setting. You get more of the feedback. You can start to take advantage of those other error conditions, and to do that is Amazon FreeRTOS. Where do I reckon you should go next? If you're not a hardware person, play with some hardware. These are the two I'd probably start with. This is one I was talking about earlier. This one here, like I said, it is stupid cheap compared to how much microcontrollers used to be anyway. This one here will cost you $16 Australian, and you can have a world of fun with it if that's your type of thing. I'd also strongly recommend if you want to get some inspiration and you want to do something that's a bit cooler or a bit interactive, art projects. Unfortunately, Halloween's just been. Electronics can be a fun Halloween project sometimes. But Adafruit are fantastic, and they put a lot of effort into the open source software and hardware community, so I'd recommend them as well. That's me. Feel free to follow me on all those things, and back to you in the studio.